All right. Nice to see you all. My name is Harrie Oosterhuis. You can call me Harrie. That's easier to pronounce in English, and it sounds right enough for me. I'm gonna give. I'll say a bit about myself actually before I get into the lecture. So I'm an assistant professor at the Radboud University. Radboud University is also in this country, but it's about 2 hours away. So for Dutch people, it's very far. From different countries, that might not be that much. But actually, I live here, so today was a very easy day for me to get to work. So that was nice. I'm happy to see you here, and I want to talk about. So I'm going to talk about learning to rank. I thought it would be good to start by asking who of you would say that they're already quite familiar with learning to rank. So the people here who would be quite familiar with learning to rank. We have a couple. Who has had a lecture on learning to rank before? Is anyone? Okay, that's less people than I thought. That's actually good. But I'm going to say for the people who already heard me talk about this or have seen a different lecture on learning to rank, I have sort of updated this material. So it's still about the most important, the fundamentals of learning to rank. But I'm going to try and give you my perspective on it, or sort of an updated perspective. So it should still be interesting if you already know a lot about learning to rank. And if you don't, then this would hopefully be a very good introduction. Okay, I know this is almost the end of the day. I think this lecture and a hackathon is everything between you and a tour through a brewery. I don't think I can compete with the brewery, obviously. So what I'm going to do is I'm going to keep it light. I don't want to make it too dense. I'm going to try and talk for about an hour, and then afterwards we're going to give you a practical assignment so that you can try and implement these methods yourself, because I think it's the best way to learn about learning to rank. Just briefly, what I'll be talking about. So I'll introduce sort of the setting, right? I want to say a little bit about how we should categorize learning to rank methods. This is really where I think my opinion and most of the people, when they teach learning to rank, differ. Then I'll go into sort of the different families. I'm not going to go into many methods. This is not a survey, right? I just want to give you the most important ideas, but don't want to make it too dense. Then we have a practical session and conclusion. And I now realize that I'm actually going to do the conclusion before the practical session, but I forgot to update this slide, just so you know. Okay, and I would also like it further to be somewhat interactive. So I'll ask you some questions at some point, and I'll give you plenty of opportunity to ask me questions. So be prepared, I guess, for that. Okay, so let's start. What is the setting that we're talking about, or the problem that learning to rank methods tackle? This is really, in the web search setting, you can think of this as sort of the last stage in the ranking pipeline. So a lot of the methods that you've talked about are about how to represent web documents or certain features of web documents. Now, the final stage, when we sort of have all that information of the final documents that we want to rank, is represented here on the left. Right, so we have our features, we have our things like BM25, TF-IDF. Your large language model may have said something about this document and the query. You may have information from a transformer, but also things like spam-based features. Are we looking at a spam document? Is the document in the right language? Is it the language of the user? Those kinds of features, or whatever information may be relevant to whether this document is good for the current query. We represent our document by features, and what we are going to do is apply a scoring function. So for each document, we want an individual score. That's the next column you see here. And based on those scores, we're going to sort, and this sorting is going to determine the ordering in which the documents will be displayed to the user. Right, so this is really the final step here. The reason we want individual scores, by the way, is for scalability. It could be that we're ranking still thousands of documents here. So in order to be scalable, we want to sort of be able to parallelize this. That's why we have these individual scores. Okay, so This is what happens in a search engine. But if you're looking somewhere else, let's say that you're looking to buy something, maybe some books on your favorite e-commerce website, you're going to end up with a similar system. So in the final stage, there's again, maybe there's different features this time, right? In this context, maybe, I don't know, the price of a book or whether it's on sale or not may be relevant. But again, there's a ranking system that converts those features into scores, orders the items, in this case, maybe products, and presents them to the user in an order. Here, by the way, we're no longer working with a top-down list, but more in a grid-based system. Again, there's still a ranking system behind this. And then lastly, as Sasha already alluded to in his presentation, a lot of recommender systems also have this in their final stage. So if you open, for instance, this was a homepage of YouTube. I don't have insider knowledge here, but I'm very sure that I'm almost certain that that last stage here again is a ranking system. Similar for any other kind of media you're looking for. So social media does this as well, etc. I think you can think of many situations where you see a list of recommendations and search results. There's going to be a ranking system there. So these ranking systems are really the basis for a lot of search and recommendation systems, very important for the navigation of really large collections, and very important to user satisfaction as well. So keeping users engaged, really the ranking system plays a big role in there. That's why it's very important that these things work very well. So we're going to talk about how to optimize them. And the reason it's well studied is because it's so important. The usual goal here, the one I'm going to focus on in this lecture, is to put the most relevant items on top of the ranking, right? Users expect that if you're looking for something, that what you're looking for is on the top. Similarly for recommendations, I guess previous days with the summer school have been all about doing that. But there are also other objectives. I'm not going to go into that here. I think you'll hear more about them tomorrow when it's more about fairness. But there's also other objectives like diversity, novelty, and fairness, where we don't just want to put the best items on top. We also want to consider sort of the list as a whole. I'm just going to focus on putting the most relevant items on top for this lecture. Okay. Then the learning to rank sort of overview looks like this, right? So I'm not talking now about serving the ranking, but how to optimize it. On the left, it's the same, right? We start with documents. I'm going to talk about this in the terms of web search, but I just want you to remember you can also apply this to product search or recommendation, as I showed before. Just to keep things simple, we'll call these documents. We have our features, we have our scores, right? We have our current scoring function. So the current model sort of did this step. We then have our ranking, the ranking of the current model. And then for each document, I'm going to assume there's a relevance label. So that means there was someone there who, a judge or someone who, when creating the data set, has said, this document for this query, it's pretty good, this one is very good, these two are really bad, you should, and this one is okay, right? So this tells us how good our current ranking is. We then compute a loss function, right? The loss function tells us, also should tell us how good our ranking is. And we can perform gradient descent, right? So this is basically quite basic machine learning, except we now have this ranking step here in the middle. So this is what we're going to look at today. I'm going to talk about this part on the right here. This is actually the tricky part, as you'll see in a bit. Before we continue, I do want to mention that there are many cases where you don't have these labels. So there's also a whole sub area within learning to rank, which is to do learning to rank from user interactions. So most of my research is actually about this problem. Because we have limited time today, I'm not going to go into that part, but everything I say here is still applicable. So all the learning to rank methods that I discussed today are also in use when you're learning from user interactions. Okay, so my first question to you is, what do you think is the most unique challenge in learning to rank? What is sort of the characteristic problem that we have in learning to rank that we maybe not have in other machine learning problems that we have to overcome? Yes, David.
We're dealing with a ranked list of items.
Indeed, we're dealing with a ranked list. So it's a very good start, right? Learning to rank, the ranking part makes it unique, right? Not the learning part. What is it about ranking that would make it a challenge to optimize it? Yes?
Ranking is something that is relative, so we want to normalize like using only the differences. So if you're like large size is too low, you have like if you do not compare with the relevant item, maybe it's a bit the same problem.
Yeah. So it's yes, so we're on the right track. So you're saying ranking is relative. It depends. It's not just about one score, it's about all the scores together. That's right. I want to be a bit more precise. You also had an idea, yeah?
So in the ranking base, so what if today, which is first, it might not be the first tomorrow or in the so temporality, right?
Yes, yeah. Okay, so yes, what is the best ranking changes very often, and so these data sets aren't perfect. The labels I'm mentioning, I'm going to assume for now they are. So you're very much correct. That's not what I'm getting at. I'm saying, let's say someone gives you, here's some items. Here are the labels. I want them in this order, and you try and optimize the model to do that. What is the difficulty run into? Yes.
The permutation space is huge. I mean, you have with 10 or which.
Okay, the permutation space, yeah, that's also a very, okay, that's also one of the unique problems. It's not the one I wanted to bring up first, but you are right. Okay, I want you to compare this with normally, right, when you do regression. What does the loss look like? I have a picture of that, actually. It looks something like this, right? Like if I lose mean squared error, it's going to look something like that. If I try to optimize, let's say, precision or DCG, what is the loss function going to look like? Right, you can make a drawing, but I'll give you the answer. So this is what I was trying to get at was the real big challenge. What all these learning to rank methods are going to be about is that at some point there's a sorting function. You can also think of it as a ranked function, like where does an item end up in the ranking, that we want to optimize. But that function is not going to be smooth. It's going to be mostly flat, and it's going to be discontinuous. So this is like your worst case scenario when you're trying to optimize gradient-based optimization, because there's no small steps that you can follow. To illustrate this point, let me make a drawing. Do I have a, here we go. Let's say that I have 4 documents, right? So we'll call them D1, D2, and I'm going to write down S for the score of the first document. I'm going to say S1. That's going to be my x-axis. Y is going to be the rank. Let me draw it a bit bigger. The rank of D1. Now, I can put, let's say, put S2 over here, put S3 over there, S4 over here. Can you already imagine what the loss function is going to do? Right. So let's say I'm sorting descendingly. So the highest score first, right? Over here, the rank is going to be, what's the rank going to be all the way over here? If I have the smallest possible score for 1. 4, yes, so it's going to be up here. And then if I move a bit to the right, it's going to stay the same, right? So when is it going to change? At what point will the rank of this document change? Yeah, when it reaches the second score, exactly. So I don't know where that is exactly, but somewhere over here. And then now we're at the next rank. So now we're over here. So now I can, right? So it's somewhere over there. So this is my function, right? You can think if you think about precision, right? Precision, if I do precision at 2, then it's going to be a function where it's 0 over here, it's 1 over there. But you can see the real problem here is this is a nightmare, right? Because over here you have no gradient. When there's a change, it's like undefined. We don't really know what to do here. So I can't just plug this function into PyTorch and say, please optimize this for me. It won't work. There's no gradient for it to work with. I mean, it will tell you there's no gradient. There is a gradient. It's just the gradient is nothing you can really use in stochastic gradient descent. So this is really the core problem that we have in learning to rank. And each of the methods that I'll talk about is going to solve this in a different way. And that's what's going to make them unique. All right. So the question that I wanted to start with was I wanted to say something about how we should categorize learn to rank methods. This is very often when you have a learn to rank lecture, what people start with or what people mention. Now, a lot of you haven't had that before, so maybe it's not as groundbreaking what I'm saying here, but I would actually rephrase the question in, should we categorize learn to rank methods at all? What I mean by that is, in most existing works, if you after this you're going to read up about learning to rank, they're going to talk about point-wise, pairwise, and list-wise learning to rank. And usually they talk about them as if they're non-overlapping categories. Like the method is either point-wise, either pairwise, or either list-wise. But if you read a lot of these papers, which I had to do for my career, right? You're going to find out that there's not a very clear, consistently used definition for these terms. So different papers talk differently. One paper will place a method like lambda mart or lambda rank in the pairwise categories other than the listwise categories, but they'll still act like these are like completely separate categories. So this is not clear what they mean by that, and when people talk to each other with using these words, I usually don't know what to make of that. I usually have to ask them what they actually mean. So I don't think it's very useful the way that people have been talking about this. And since I get to stand for an international audience with PhD students, I thought it's a good moment, like a way to get rid of that by trying to convince you to think about these terms not as sort of separate categories, but as properties that methods have. So what I'm going to do in the rest of this lecture is I'm going to talk about the different categories or the important properties that I think are important in these methods. But I want you to think about them as sort of properties, so check marks, not separate categories. Okay. Now we are ready to get into specific methods, but I want to make sure that you don't have any questions for me that are relevant right now. If you have, I'd be very happy to answer them. Do you have any questions for me? Okay. All right, I hope that means everything is clear. Well, anyway. So I'm going to start with pointwise learning to rank. I think you may have heard this term pointwise thrown around already quite a bit. What we usually mean by that is that we approach learning to rank as a classification or regression problem. So that's not exactly right. So some people say when they say pointwise, they mean that you take each prediction individually instead of thinking about what they do in the ranking. So instead of these relative parts, we ignore it. And what we end up with is basically just classification or regression. For example, mean squared error is very common. This is a bit of a misnomer because I've ignored the normalization term. That's because it makes my life easier on the next slide. But if you imagine that we're dividing by the number of points there, we have mean squared error. And yeah, we end up with a loss like this. So this is very nice. It's very smooth. It's easy to optimize. This is typically the first thing that you might try, right? If you know machine learning, you've almost certainly seen the mean squared error before, optimized it before. So it makes sense that it's the first thing that you try. That's also what happened in the literature. So this citation goes all the way to 1989. I think Sasha beat me with a citation to 1960 on his previous presentation.
Yeah.
But usually 1989 is quite far for okay, so I hope that's quite clear, right? I think you've seen a lot of machine learning already. We're just gonna, for each document, we're going to look at the difference between the label and the predicted score. And we're going to take the square difference. And then our loss function is going to say, for instance, if the label is 1, let's make the score also 1. If the label is 0, let's also try and get the label to 0. Right? Very, very straightforward. I would visualize it something like this. Here's an example. We have 5 documents. The document all the way on the left is the only relevant document. I'm just keeping things binary here for simplicity. We have our predicted scores here. And then we have our error, like how far away is the score from the label. You square each of those and you take the average and you have your mean squared error. All right. Okay, so it's easy to understand. My question to you is now, what is sort of the main limitation of this approach? You could also phrase it as what is wrong with the pointwise method. And I'm looking for sort of a fundamental problem. Yes.
I think you're trying to make the outcome very extreme. So you're trying to push the result either to 0 or to 1, which is might be bad for ordering the results.
Yes.
If something is somewhat relevant and you want it to be on position 4 of the ranking in the end, this might not be optimal.
Okay, I'm repeating your answer for the people online, but you were saying it's going to push the scores to the extreme, like all the way 0 to 1, and that's not necessarily what we want, or not necessarily best for the ranking. Yes, we are on the right track. I'm looking for an answer that's a bit more, how do you say, general or fundamental. In the back, yes, Thijs? Yeah.
So in ranking, you want to compare stuff and put them in the right order. And with this approach, you're not really comparing anything. You just take everything on its own.
Yes. Yeah. So the answer here was in ranking, we are thinking about ordering things, and ordering is a sort of, as I said before, is a relative thing. Here, if I go back one slide, right, we see nothing of that, right? We're completely ignoring. This doesn't look like ranking at all. We're basically just doing regression here. We're ignoring the whole ranking part. Okay, let me show you, give an example sort of to understand what's going on here. So here I have, is this the same example? No, but it's almost the same example. So we have 5 documents, but now the first one has a score of 0.6. This is the right document, this is the relevant document. Everything else is a score of 0.5. And the ranking that this results in is the one we want, right? The relevant document is all the way in front. What is the squared error here? So if we don't take the mean to make our life a bit easier, okay? This is a bit, so I know the answer, of course, but basically if we take 0.5 squared, we have 0.25, right? A quarter. We have 4 of those, so that sums up to 1. Here, the error is 0.4. That's going to be 0.16, right? Okay, there we go. All right, 1.16. All right, nothing groundbreaking here. But basically, I just want to show you we have the right ranking, we have the loss of 1.16. Here is another ranking. This time, it's the wrong one. The relevant document has a score of 0.1. Everything else is a score of 0.2. What is the loss function here? Or what's the value of the loss function here? This one is a bit more tricky. If you have a calculator in front of you, you could probably do it very easily. I'll just give you the answer. It's 0.97. All right. What would be the problem here? Can you see the problem? So, sorry? Exactly. So in this case, the ranking is perfect, but we can decrease the loss by making the ranking worse, right? So that means our loss does not correlate with our ranking performance, and that's a very bad place to be in, because when we're doing optimization, we assume that if we decrease the loss, our ranking gets better. Now, it is true that if the loss is 0, then we solve the ranking problem. But in practice, the loss is never going to be 0. So the model is going to compromise. It's going to have to choose sort of what are the parameters of the model that give you the best performance. And it does that under the assumption that a lower loss means better performance. But that's not the case. So the pointwise losses don't optimize ranking quality directly. We don't have a correlation between loss and ranking. This is a big problem because this is usually what stochastic gradient descent assumes that we have. So there's a mismatch between the pointwise losses and the actual ranking quality. I see I made a typo here, sorry for that. What you can remember basically is ranking is not a regression or a classification problem. So while it's easy to apply, we're not really optimizing the ranking here. Okay. That brings us to the next family of methods, which are pairwise long-range rank methods. And my guess is that you've seen a couple of these already because they're very popular still in when you're dealing with very large models like transformers or large language models. The idea here for pairwise loss is that we minimize the average number of pairwise inversions. And what that means is that we look at how many of the document pairs, if I have 2 documents, how many appear in the wrong order in my ranking. Right, so how often do I put a document that should be in front of another document behind that document, basically. And typical pairwise losses have this form. So to keep things short, I'm going to say S is the score for document I. And I'm going to sum over every pair of documents where one has a label that's greater than the other. So I is more relevant than J. And we take the difference in that score and we put it in some function. There's many different functions that you can apply here. There are things like hinge losses that you can use that were very popular back in the day. Nowadays, or really the most popular has become RankNet. So RankNet has a weird, this is related to regular telling models, but let's ignore all of that. What it basically does is it puts it inside a log where with e to the power, so it's always a positive number. This log is going to make sure that this shape doesn't explode. If you were to just take the difference, like this is what happens in a hinge loss, you would basically get a loss that grows linearly with the difference. That means that one pair can really dominate the loss. You put it in the log, it doesn't grow as fastly. It also approximates 0. So if your scores are already in the right order, pushing them even further apart doesn't give you that much in the loss. So we focus on the pairs that are in the wrong order. Anyway, I don't think those details are very important. What I mainly want you to remember is that in pairwise loss, we're thinking about minimizing the number of inversions. The reason that one of the big benefits of this approach is that you can parallelize this over the pairs, right? So if you're training a very big model that is hard to fit on your GPU or your TPU, then instead of having the whole list, as some of the later methods have, you only need to have 2 documents at once. So you can, so it scales very well. And that's why you see it a lot in sort of natural language kind of models or large language models. Okay. Very straightforward idea. Another way to visualize this is to think about it I like to think about this in sort of broadcasting matrices. I bring this up because it's also going to help you if you want to implement them. But here I have these 5 documents. 2 are relevant. These are the same list, but it's transposed, right? So, and then I can compare each of these points here is the difference between the 2. So each of these represents a pair, right? So the diagonal is comparing documents with themselves. That's not very interesting. But this here tells me that 1 is greater than 0. So document 1 should be above document 2. And the same for 4 and 5, etc. Right? So we have this matrix made from the labels. We can do something similar with the scores, right? So here are the scores that our model has given us. And we can again make this matrix. but now we can see how many times we're wrong, right? So over here, these two arrows, they're pointing in the wrong direction. They're preferring, so our model is preferring ranking 5 over 1 and 3, whereas we see that actually it should be the other way around. So it's basically what a pairwise loss does. We take all the pairs, we look at how often are we wrong. Okay. Straightforward idea. I have the same question for you. What's the main limitation of pairwise learning to rank? So if we take this approach, what is sort of the fundamental thing that we're still missing here? Right, we can see an improvement over pointwise learning to rank for sure, where we were completely ignoring ranking at all. We're now looking at pairwise differences, but that still isn't what we really want. My question to you is sort of what is the main thing that we're missing here? Anyone like to guess? Oh, thanks. Yes.
You have to make very many comparisons to create full rank list because you have to compare all things.
That's true. So one of the downsides is that we have to do a lot of comparisons here. So that's what I was alluding to earlier. If you, for instance, if you get this out of a very big model, even like very big transformer models, and you have a list of 1,000 documents, it's going to be paying you to compute this, and you probably can't do it with one GPU at once. So that's why. But on the other hand, you can parallelize it. So you can look at one pair at a time. So that's the solution that's usually used. So we can kind of overcome that. We also have a quadratic complexity. That's also fine. And it's only during training, right? So, but that's not what I'm getting at. I think my problem is it's in a similar. You can think about the problem we had with pointwise learning to rank. It's kind of a similar problem here, but it's different because we have a different approach now. Okay, I'll give you an example, and maybe it helps you to see what I'm getting at. So here's a ranking, right? So the ranking here, it's definitely not perfect. We have 2 relevant documents. One is all the way in the front, and the other one is all the way in the back. Right? I have 11 documents in total. Best documents are in the front, all the way in the back. Okay. Here is another ranking. Now the 2 documents are in the middle. Right? Who thinks of these 2 rankings that the first one is better than the second one? So who thinks ranking 1 is better than ranking 2? Okay, that's most of you. Who thinks ranking 2 is better than ranking 1? Okay, we have 1 person. And who doesn't know? Who's like, okay, all right, so sorry. Okay, so most people agree that, or let's say, usually when I ask the question, everyone likes ranking 1, except for a few people. Most of those people usually don't really know how to choose, and there's very few people who like ranking 2. So your PhD students, when I teach to, or most of your PhD students, when I teach to younger students, the younger they are, the more likely they are to claim that they like ranking 2. I don't always believe them. You can take this example, you can make it more extreme. So I could have done this with 100 documents, where in ranking 1, the relevant documents at the front and start. Ranking 2, they're in the middle. Usually people agree that that's really bad, right? It's rather to have 1 good document all the way in the front than the first documents to be good at rank 50. So let's agree that ranking 1 is better. Yes, do you want to say something? Yeah.
So I prefer ranking 2 because
Okay.
I guess in total of like the current tool-based model, right? You really need to increase the recall, and if you have a very long context, ranking 2 will give you better recall than ranking 1.
Yeah, that's right. Ranking 2 gives I guess a better recall. If you really need the 100% recall, that's right. That's a case where you would prefer it. But I'm more thinking about if you're searching for something, you're just like, okay, I'm looking for the next bus to the brewery. Would you rather have like a good answer immediately, or would you have to wait? So that's usually the setting I'm thinking in. But you're free to have your opinion, right? It's not up to me to say that you're wrong. What I do want to point out for everyone else who agrees with me that ranking 1 is better, is if we count the number of pairs that we get correct, we have 9 correct at the top, right? So we have this one is in front of 9 documents that are worse than it. At the bottom, we have 10 pairs correct because we have 2 in front of 5. Now, again, if I go from 11 documents to 100, this same pattern follows. So can you see the problem that we have with pairwise learning to rank?
Not 1,000 documents and the correct queries in the middle. You can just comparing pairs, not really.
Yes. Yes, yeah. So the problem is indeed that we're comparing pairs irrespective of the rest of the ranking. And what happens is that the loss might say, well, like fixing pairs is what we're thinking about. So it could be that in order to fix some problem here at the end, we are ruining the beginning completely. So a pairwise loss could sort of, in order to get the top 5 right, in order to get the last 5 documents in the right position, it could completely ruin the top 5. Whereas anything we know about users, they want the top 5 to be right, not the bottom 5. So pairwise learn to rank functions minimize the number of incorrect inversions. So they maximize the number of pairs that are correctly, but not every pair is equally important. It's more important to have these pairs correct at the start of the ranking than at the bottom of the ranking. And this is just not something that pairwise learning to rank looks at. So the problem is if we're just pairwise, right? If we don't have the properties that I'm going to talk about next, we're not considering the entire ranking still, and we could still be messing up the complete ranking to get some pairs correct. So this is why we usually don't want to do pairwise, but again, there are many places where we can't really do more. But in many cases we can. And sort of the next development, the next thing that came after listwise learning to rank, and this is usually where the lectures sort of stop in their categories, was listwise learning to rank. So this came right after pairwise learning to rank. You can see the title here is from pairwise to listwise. So this was kind of treated as sort of the last family of learning to rank methods in 2007. The idea is that we're going to consider the entire ranking. So usually when people say listwise learning to rank, they mean I have a loss function that thinks of the complete ranking. It doesn't split up in pairs or in individual documents. We look at the entire thing. The first method, which they introduced as the listwise method, this again makes it complicated for us to talk about, is took a softmax Plackett-Luce distribution. So it's actually a Plackett-Luce distribution. Nowadays, with everyone doing deep learning, I find it easier to call it, to use the word softmax because it's very similar. What we do here is we have a probability now. So it's a probability of sampling a document. We take the score of the documents, we take e to the power of the score to make sure this is a positive number, and then we divide by the sum of the other scores, where we also took e to the power of their scores. This is just a softmax function, right? It's the easiest way to think about it. And we rank then by sampling without replacement. So if I'm ranking here 2, 1, 4, 3, my first probability is the score of 2 divided by the score of all the other 4 items. The next one is a score of 1, right? 1 was the second document, divided by the documents that are left. So now 2 has been removed here. Then we have 4, there's only 2 left, 3 and 4. And lastly, we have 3 divided by 3. This is just 1, but just for completion's sake, we get it here because it's the last one left. So this gives us a valid probability distribution over rankings. And what's important here is that you cannot break this down into pairs. So you cannot write this loss as a pairwise function unless you're really messing with the structure, right? So, but the function I gave, the form I gave before cannot handle this shape. And the idea is that we now have this probability approximation, right? So in order to maximize this, we really need the score of 2 to be greater than 1, 2, 3, and 4. Here it needs 1 needs to be greater than 3 and 4, 4 needs to be greater than 3 and 4, and this doesn't really do anything. So if we optimize this, it will get the ordering more correctly. It will get the ordering correct. And we would also get a probabilistic model if we would like that. That's not really the goal for this lecture. But here we have the first method that really takes the entire ranking into account and not just pairs. Do you have any, is that clear? Do you have any questions about this before I continue? Yes.
What
Yeah.
is the E? What is E?
E is just a constant, right? So the natural number, right? Yeah. So you can use anything with people use E. It's easy when you take the derivation because
What S? The position?
S is the score of the document. So that's from that slide over here, right? So S is if I take my model, I apply it to the features, I get S as the score. Right. So you can think of it as the output of your model, right? So my model gave score S to document SI to document. Yes. Yeah.
So let's say your ground truth readings for D, like D3, D4, D1 is 4.
We'll get there. We'll get there. Okay. I know what you want to say, but that's the next thing. So, but I just want to make sure that people understand this method. Because what you're getting at is mine. Oh well. Anyway, okay. So this is how we model the ranking. What you're getting at is one more slide away. So here we have the same thing, right? I just for complete sake, this again with the model. What the list method assumes to optimize this is that there is a best ranking. That's in this case R star. So there is a best ranking. You can sort according to your labels. You get a ranking out of that, and then we maximize the probability of that ranking. This is basically just the negative log likelihood. We just tell our losses now basically the log score of that model, and then we take minus because we need to optimize. This is what we're going to minimize so that the direction is correct. So we use the model to maximize the probability of what we think is the best ranking, and then get it out. So this is the listnet method. Okay. All right. So my question again is, what is the main limitation of this approach? Right. So I'm optimizing my model now is a probability over rankings. I have one ranking that I know is the best ranking. I'm going to maximize my probability in that direction. Yes.
So I guess in many cases you can only access to the score, the label, what is the rankingness. And there are some variants that the ranking given the same score.
So there are definitely cases where multiple rankings are the best ranking. Very often, right? Very often we have multiple documents that are equally well. Is that what you're getting at? Yes. So you could adapt the method to sort of pick one of them or pick all of them. There are solutions to that. But you're getting there. Like it is related to what I think is the fundamental problem. But I want to go one step further. So you've identified a part of the problem, but I think the problem is even bigger than that.
Computation problem. So into
No, it's the permutation problem could be an issue if we take that approach where you try to optimize all these different rankings. That's not what I'm getting at here. Did you? Oh, yes. So there is a computation problem that you do need the whole list in memory, but in many cases that's not a problem. So in many cases these features are something you can pre-process, pre-compute. When you do ranking inference, right? When you have this in production, you also need all these scores. So it's not. There's many cases where people have done this. This has also been applied to BERT models, but you need a lot of resources. That's basically the. But the computation problem is not what I'm getting at. I'm more thinking in theory. So can you remember what is our goal, right? What are we trying? What did I start the lecture with? What are we trying to optimize here? You remember I made a drawing and.
greedy.
Sorry?
It's greedy.
It's greedy. Is list-wise greedy? I'm not sure if it's not exactly what I mean, but sure. But what are you thinking about? Yes.
Like it is not flat. The function could be pretty strength.
I see. The shape of the function. Yeah, I'm not sure if the shape of the function is the issue here. But do you remember what are we okay, how do we evaluate our ranking model? Right, what do we use to evaluate our, yes, yeah.
You can use, for example, the relevance between the documents ranked and equated. But also you say about other goals like diversity.
That's, yes, so I mentioned diversity. I'm ignoring those for this lecture, right? But about getting the relevant items first, right? So how do we usually, like if I have two ranking models and I want to know which one does it better, what am I going to look at? I'm not going to look at the sorting function, right? I'm going to use the sorting function, but I'm going to compute something else, right? Yes, for evaluation, how do we call a loss function for evaluation? You know it's a metric, right? Metric, right? So that's exactly. So precision is one. The other one that's really commonly used that I mentioned already. Recall, discounted cumulative gain. So we have a lot of metrics, and the metrics are what we care about. We want to have sort of the highest scoring metrics. Now, my point is basically, where is the metric in this, right? What are we optimizing precision? Are we optimizing DCG? All right, none of that is in here. We're only thinking about getting that one ranking out of it, but it's not directly related to our metric. So it's not quite like we are optimizing an ordering of sorts, but we don't know how this thing makes a compromise. We don't know whether the choices it makes are better for our metric or not. Again, for instance, if I care about my precision at K, let's say precision at 2, right? Then I really don't care about this last part, for instance. I don't care about my last, like we want to rank 2, but this loss doesn't know that. This loss just does the whole thing, the entire ranking. So it's not informed by our metric, while our metric is really what we're trying to optimize. So you may have noticed that every time I ask this question, the answer has been kind of the same. It's that my loss function and the thing I actually want to optimize don't correlate or are not the same thing. So, but the ways in which they differ have been different every time. So, yeah, it's the same thing. So there's no ranking metric involved here. Do you have questions for me? So about this part? Yes, yeah.
I mean, likelihood can be a metric, right?
Sure, yeah. Okay. Okay, I guess I stand corrected. Thank you. Yeah, so this rightly points out that you could have log likelihood as your metric, and then we are indeed optimizing what we want. Sure, it's just not like I have never seen anyone do that, but theoretically speaking, it could be. But if we think about any of the ranking metrics that are usually used, it's not this one, right? Usually we're optimizing a deterministic model where likelihood doesn't exist.
Why your probability, why your desire, you should get expectation.
Exactly, yes, we will. We will. Yes. Okay. Yeah, I mean, if you want, I'm happy to, okay. All right. So, as I said before, if you look up, if you're going to read a Learn to Rank book, or if you're going to read a lecture, the list usually ends at listwise. It's kind of like after listwise we are done. My point is that no, even inside listwise we have these things that still aren't there yet. We need to go further, and this has been done before, but they usually so this is where the standard categorization ends. But I think the next property to think about that's important is metric-based learning to rank. So to tackle this problem exactly, we want to optimize a metric, so that metric should be reflected in our loss. So I want to be able to say I have a specific ranking metric, can also be a weighted average of ranking metrics that I want to optimize, and have a method that does that. Not a method that will do the same regardless of what I'm trying to optimize, right? So the thing here, why I think usually this distinction is not made, is because ranking methods are almost always listwise, in the sense that if you want to calculate precision or DCG or recall, you have to do a complete ranking before you can compute it. So if you're going to base your loss on a ranking metric, it's probably also going to be listwise. Again, someone can choose. There are also pairwise ranking metrics. They're not very popular, but they do exist. In those cases, this doesn't apply. You could assume, and you probably never be wrong in your lifetime, that if you see a metric-based method, it's also a listwise method. But I put that caveat in there. So the most famous method that is both listwise and metric-based is lambda mart. Lambda mart is just an application of lambda rank to random forests or gradient boosted decision trees. I'm going to talk about lambda rank because that's where the loss function was introduced and originally applied to neural networks. What you see here in this loss function, this first part is just the pairwise loss of rank net, right? You remember we were summing over pairs where the notation has changed a bit, but this means document 1 is better than document J. So this document is better than document J. Again, we have this log and we have this difference between the scores of the two models, so the output of our scoring function, and then some parameters e to the power. So this is the pairwise loss again. But the crucial difference is that instead of treating each pair equally, we think about how important each pairwise inversion is by multiplying it with this weight here. So this weight, you can do it for any metric. I'm doing DCG right here. That's most commonly used. This weight is the difference in DCG if you were to swap these two items. So I take my ranking, I leave everything the same. I swap these two items. What's the difference in DCG that I will get there? And then we take the absolute difference because we're pushing both pairs in the same direction or in the opposite direction. So you can think about this. If you change two documents at the end of a ranking, so I guess you're on the opposite side, so it should be here. If you're taking two rankings at the end of a ranking, maybe let's do it vertically at the end of a ranking, right? If it's very far down the list, it's not going to affect very much because the weights there are very small. If you go to the top of the ranking and you change number 1 and 2, it's going to be the enormous weight, right? It's going to be quite a big difference. If you take 1 and you take the bottom rank, it's going to be even bigger. But the point is that this weight will automatically sort of say, okay, these pairs at the bottom of my ranking, I don't really care that much about their exact ordering. But if I have a document down here that needs to be up there, then I'm going to assign a big weight to that pair. Now, the story behind this is quite interesting to me in the sense that how did people find out that this is the way you should do it? Well, in the original paper, they admit that they had an engineer, like they recognized the problem, all pairs are treated equally, we need a solution, what should the weights be? And then someone at the right time, I guess, tried this weight and it worked really well. And this became sort of the state of the art for the next 18 years or so. I think in certain benchmarks, this still is up there with sort of a standard baseline that you include. But it was really sort of someone who just thought this sounds like a good idea to address this problem. About 6 years ago, someone found out that this is actually a lower bound on the DCG metric. So there seems to be some theoretical reason why it works, but originally it was just someone who thought, okay, this makes sense, someone should try this, and then found out it worked really well. So that's places where machine learning is very close to engineering. I don't know if I said it explicitly enough, but these weights are treated as constants by the gradient. So we're not going to take our gradient into these weights. We're just treating them as constants during learning. So what happens is when we compute the loss function, we create our ranking. For each pair, we look at what happens when we swap them. We use that as a constant weight and then just apply the pairwise loss as a weighted average with those weights. Is that clear? So you don't have to understand why we're doing this in much detail. You have to understand the weighting is important. But again, it's kind of an engineering trick, really. What I wanted to say about this, so yeah, it's the most important baseline. sorry, I'm drawing a blank. This was yeah, I guess it's not important if I can't think of it. Oh yeah, the categorization. So this is the method where if you look at different works, you'll find it treated either as a pairwise method or a listwise method. It's often considered a pairwise method because, well, this is clearly is a pairwise loss. But others can say, well, it's a listwise method because in order to compute this constant here, you have to consider the entire ranking. So my opinion is we should just accept that it's both a pairwise and a listwise method, and we should mean what we talk about. So if you talk about computational complexity, it's important that we have to go over all pairs, which makes it a quadratic loss function. In that sense, it's definitely pairwise. But it's also listwise in the sense that we do need an entire ranking. Anyway, that's my take here. If I would bring this up to sort of people that are in the field longer than me, we might have to fight over it. But for you, it's easy because I'm the first one maybe to introduce this, so you don't have a strong opinion about this yet. But that's my take there. Yes, yeah.
So you couldn't do this when you only observe this, like the previous maximum ranking test. The previous method can be applied when you only observe the rank test, not the score. There you need to know the score.
Oh, you mean in the previous method, we only need to know what the best ranking is, right?
Yeah.
And now we need to know this metric. Yes, that's right. So if there are cases where you only know this is the ranking I want, and then you don't have a ranking metric to optimize, yeah, you can't really do this. No, then the other one would make sense. But usually in the learn to rank setting, that's not the case. There might be other places where that is the case, right? I mean, if you're generating language or something, that might be a different for your learning permutations. Yeah, but that's not what I'm talking about here. Okay. This is a very complicated way. Luckily, recently, people have thought of other ways to do this ranking, optimizing rank rings. And I think the most important one right now is to do rank metric approximation. It's very general. The idea here is that rank function, we can actually approximate that rank function in a differentiable way, and then just use it in our metric. So I'll say, this looks complicated, it's not that complicated. The rank of a document is basically 1 plus 1 for every other document where the score of the other document is greater than the other one. I think we're ranking in the other direction. But anyway, you can count the rank of a document is 1 plus how many documents are in front of it, right? So you can use this. You can use an indicator function for that to write that down. So here I've just written. That's what this says is 1 plus every other document that has a score greater than this document. Okay. Now this indicator function here, you can actually approximate it or upper bound it with a sigmoid function. So you can say 1 divided by 1 plus the difference between those two. And in the extremes, this is going to give you 0 or 1. And in between, so it's smooth, but in the extremes, it's pretty good approximation. And it's completely differentiable. And the nice thing is that it always gives you a number greater than the rank, I think. It's a pretty good upper bound. Although now that I say it out loud, there might be some, I'm pretty sure it's an upper bound. There might be some edge cases I'm ignoring here, but we can ignore those as well. So basically, I can perform this, I can take this function here, which is based on a sigmoid, and it's going to give me something pretty similar to the rank of the document, but it's probably going to be a bit greater than the rank, but it's differentiable. So I can use it to do optimization. Now I can take my metric. So here is DCG, and I can just plug in this rank function here. So it's not the real rank function, but the upper bound. Now I have something that I can optimize that's differentiable, and everything looks great, right? It's very easy to implement. Again, it looks kind of pairwise because we're summing over pairs, but it's also considering the entire ranking. So it's also listwise, it's metric based. So this looks great. There are some limitations here as well. So we kind of assume that our metric is monotonic and smoothly decreases. If you do this for precision, for instance, it won't work because, again, the weights are going to be 1 or 0, and there's not the in-between area. So most of the loss function is going to be flat. This also doesn't work for things like fairness metrics. So if we just want the most relevant items to be on top, this is usually fine. If we're optimizing something where it really matters how far on top it goes, like should it be at rank 1 or should it be rank 4? This method can't do that. It's just going to push the most relevant things all the way to the top rank. Okay, but it's a very elegant way, I guess, to solve this problem, and it's very popular for that reason. Okay, it's relatively new here. It got famous again with these TensorFlow PyTorch frameworks because you can implement them very easily in those. All right, then there's one more category that I want to talk about, and I think, Sasha, this is where you wanted to go a while ago. But there's also a stochastic approach. So we've kind of talked about this already. Stochastic just means that we have some probability in there, some randomization. Inspired by reinforcement learning, we can also take our probabilistic model that we had before. If you remember that listwise model where we had a probability distribution over rankings, and then look at the expected utility. So basically, so this is how you can write that. It basically means we're going to sum over all rankings. I'm going to take the probability of that ranking coming out of my model. You remember how we computed that probability with softmax, right? Multiply it with the metric value for that ranking. And now we have an expected value of that metric that we can optimize. This is smooth, this is differentiable. So far, so good. Can anyone point out what is the big drawback from doing this, or where you would probably like what part of this would make your life very difficult if you just implemented it like this? Right, if you think about implementing this function, how far would you get before you would realize, oh, maybe this is not going to work as easily as I liked? Yes? Yeah.
So you have the variance in the estimation.
Sure. Yeah, the reinforcement learning is usually has a lot of variance. That's right, but that's already, I'm talking before that. Just getting your first gradient. How long would it take to compute the gradient in for your first batch? Yes.
Because you have to calculate all the probabilities for every document. You have to also find the DCG. Maybe.
Sure. Yeah, we have to the probability for every document, the DCG. That's doable. That's doable. But there's this other thing that is going to take a while.
Yeah, but the probabilities given the query.
That's fine. Yeah, that's just what our model gives us. That's not that's fine because we just compute the scores and we have this formula. It's linear time basically. Maybe a sorting in between. That's okay. Yeah.
That you're looking at or considering optimization for.
Yes, exactly. So this thing right here, I said it very casually, and none of you were like, I'm summing over every possible ranking, right? So that's a combinatorial nightmare. So if you have 10 documents, this already becomes very hard because you have to do 10 factorial. If you want to go to, if I have 50 documents, I'm already talking about billions of ordered higher than billions of possible rankings. So we can't do this. We just, it's never gonna, like, not in your lifetime will you be able to compute the gradient of one batch if you have a decent size of document. So we need to do something else. Luckily, from this one, it's quite easy to solve. We can just sample. You can sample very quickly from Plackett-Luce models with the gumball trick. I'm not going to go into that here. We can sample very easily. So I can just sample n rankings and then look at the average, and I have my expected utility. So the number of rankings is really enormous, and this now becomes a problem here. So this is, again, one of the unique problems of ranking, but it only shows up if you go to this type of method. For sampling, we can use the log trick. So this is the log derivative trick from reinforce. I don't know if you're all familiar with it, but I can write it down. So basically, I now have to say it correctly, but the gradient of log probability is equal to the gradient of that. Let me write it out bigger. Yes, so the probability of the log of a probability is the derivative of the probability divided by the probability. So if you plug it in there, you can see that this probability here cancels out, and we just have the log probability again. The reason we don't do that is by having this summation over all rankings and this probability here, this turns into an expectation, right? So by using the log trick, we can now write it down, or we can approximate it like this, where we sample these rankings and we use a DCG when you optimize the log probability. If you ever see reinforcement learning and you realize they're optimizing the log probability, that's because of this trick here. Now we can sample the ranking and we can optimize it. This is what's called the reinforce log derivative trick. I don't want to go into too much detail here because I think it's better to focus on other things, but it allows you to approximate the gradient. We still have an issue with variance. Computation can take a while, so there's papers specifically about that. So PL rank is something I introduced as a method to really, as quickly as we can, compute this gradient for DCG kind of metrics. I don't want to go into too much more detail here. I just want you to realize sort of that this other branch is based on reinforcement learning, where we're optimizing probabilistic models. Okay. I'll give the overview, and then we have some time for questions, and we can look at the practical lesson. So I've given you 5 important learning to rank properties. The first one is pointwise. So this really isn't learning to rank. This is just taking learning to rank and applying classification or regression. I just want you to remember that when people say pointwise, that's usually an admission of like, we should probably be doing something else, but usually because of resources we can't, so we just apply a pointwise method. Pairwise is the next sort of development in learning to rank, where we look at pair inversions. So we look at pairs of documents, whether they're in the correct order. What I want you to remember there is that these pairs ignore the complete ranking, and it can be that certain pairs are better to optimize than others. This method ignores that. Then we have the listwise property. So these are methods that consider the entire ranking, but they don't necessarily optimize the metric. So there are listwise metrics listwise losses that don't have anything to do with any metric, but still listwise. So again, I want you to, in my opinion, these are overlapping. There are pairwise methods which are always also listwise. So I think it's best to think about them in those terms. Then we have metric-based methods. So these are methods that actually take into account what we're trying to optimize, which metric. And one way of doing that very explicitly is these differentiable approximate metrics. Lastly, I talked about stochastic learning to rank. These are when we optimize a probabilistic ranking model. And so the latest work here does that with a reinforcement learning kind of approach. This also says something about where learning to rank fits it in machine learning. Like it both has links to classification and regression, but also to reinforcement learning. It's not clear exactly how we would classify that. I guess we don't have to. What I would like you to remember is what learning to rank is, right? So a way to combine these large number of features that you get for your documents to create your final ranking. The derivative of the ranking metrics are not usable for optimization. It's just not possible to take precision or DCG or recall and optimize that directly. So there is no silver bullet here. It's just, we can't do that. We need heuristics, and that's what every method does. So every method has a way to heuristically approximate this gradient in a way that we can use it for optimization. And the way that they do that is just how they differ. Right now, there's not one learning to rank method to rule them all. It would be nice if there would, then my lecture could be maybe 20 minutes, but I'm working on that for the future, I guess. But right now, there's not, we can't say like, this is the best learning to rank method. There's some like point-wise where we say, okay, you should definitely avoid this if you can. But for almost all the other methods, there are some uses for them in practice, right? So you can encounter each property you can encounter them somewhere, basically. Yeah, and think about these as properties instead of categories. Even though you will, maybe in the literature, you'll find that people do think of them as categories. All right, that's my story. So before we go to the practical session, do you have any questions for me or anything you would like to discuss? Yes.
Thanks, first of all. I'm curious. Maybe in a not so ideal setting, your data set can be very skewed and you have a lot of relevance labels for some documents.
Mm-hmm.
And then suddenly you want to rank a document that you haven't seen so often or mostly at the bottom of other rankings.
Mm-hmm.
Could it be that point-wise then outperforms these methods that optimize for lists?
All right, so if I briefly repeat the question for the audience. So you're asking, could there be cases where point-wise would be the best choice? For instance, if the data is very skewed. So something that you might see in the practical assignment is that, there are cases where it works better. It's not clear exactly when that happens. But for instance, if your training data doesn't fully resemble the way your test data looks or where you're going to apply it, all sorts of things can happen. And it could be that it's more stable, for instance. It's very rare. I think in practice, people really try to avoid the point-wise method. But there are benchmarks where it's not, we can't say pairwise is always better than point-wise, but in practice, it's kind of true. So in the end, you have to test different things. Yeah. Yes.
Okay, so for example, lambda rank is quite an old method from 2006. You said,
yeah.
And see, like in 2012, this AlexNet for image classification, and now we use neural networks, right? Like the lambda rank was already there. But
yes, lambda rank is older than AlexNet for perspective.
Yeah, but and actually, image networks also kind of list-wise competition because people are interested in like okay. So it seems that all these list-wise methods not needed for neural networks. People just use softmax, and it seems to be working. And lambda rank or like similar methods don't add much, even though when we care about this G or we call it K or something. So, what's your opinion on that? So nobody just knows how to cook it for neural networks, or you just not needed because the network itself is too generalizable.
So your question is in settings like image classification, right? Where we're I see.
So like all these, for example, non-adverbs type of models, they don't do this.
Yeah, there's not one. I don't think there's one learning to rank method to rule them all. There are settings where the difference between the methods don't matter as much. So I think you're referring to like image label, right? Where I guess we're ranking the image labels. We want the top K of the labels to have certain things in there. I think that setting is very different because we are now not making these prediction scores individually anymore, right? So here we really have the features of one document, we have one score, and then all the way at the end is when they come together. Whereas in AlexNet, you compute all of them, and then in the end you produce each score, and then it comes out. So the model before that can already think about what it's doing. I think that's a very important difference. I can't prove to you that that's the salient difference.
It doesn't seem that, for example, like all these models like model Earth 195 rank something like they also just use like percentropy, like finding percentropy or multi-class percentropy. And the idea itself is just take a lambda rank and like apply to this like people did 20 years ago. Seems to be kind of obvious, but by some reason no one does it.
Okay, right. Okay, I'll respond. I think we should take this offline because it's a very wide view. But it is surprising, but as you point out, that lambda rank was so powerful on the learning to rank benchmark, but nowhere else were people like, oh, we should do lambda rank. I think there are a few exceptions, but on the whole, that's kind of true. Yeah, I think there's something about lambda rank that makes it work very well for the web search setting. And I also think it helped field back because it was very hard to come up with alternatives because you couldn't beat the baseline, and that's what people wanted. So I have the feeling that stochastic learning to rank and putting learning to rank inside of reinforcement learning is a better way of doing it. And the problems that the reasons why learning to rank doesn't always work have more to do with the reasons why reinforcement learning methods often don't work. But it's kind of speculation, right? We don't have we can't do a direct analysis of this or a direct proof of this. Yes. Do you have a short question or?
Yeah.
Okay. Yeah.
More on, in the summer school, we also learned about re-rankers.
Mm-hmm.
It was also performing the ranking part and also learning to rank. So what is the difference? Are they in the similar direction or?
Your question is learning to rank different from re-ranking or in a re-ranking? So usually learning to rank is applied in the final stage of the re-ranking. So usually it's a cascade. Usually you have one model that goes from 1 million to or billions to millions. You have another model that goes from millions to 100,000s. And each of these models can be more complex, right? Because if you only have a couple of nanoseconds to do the millions to 100,000s. In that final stage is usually where we apply learning to rank. So usually we have about 1,000 documents left. That's when we have all the features, and that's when we can make a prediction.